Hello, we are going to start our trig application examples here. So, quick note here, be careful. You should always work in radians unless otherwise specified. So get used to really working in radians unless it says otherwise. Number one, the tide in Victoria, British Columbia reached a maximum of 3.0 meters at 2 p.m. and a minimum of 0.2 meters at 8 p.m. Sketch a sinusoidal function using time t as the number of hours after midnight. Okay. Um, the assumptions that we'll make are that this is an application, so we have to be careful on what assumptions we make. So the assumption we'll make is that this is, or sorry, this function is a perfect sinusoid. Okay? Let's go ahead and determine the A, B, C, and D values based on what we're given. Okay? And then we will sketch this. Okay, so let's go down here. Determine four sinusoidal functions that represent the change in the tide height in Victoria, BC on this day using a minimum horizontal phase shift. Okay, so before we graph it, let's think about our max and min points. At 2 p.m. So that's 14 hours after midnight, because that's the starting point, right? Okay, and then 8 p.m. that is 20 hours after midnight. All right. So at 2 p.m., 14 hours, 12, 13, 14. The tide is at 3 meters. So at a maximum of 3. So 12, 13, 14, 15, 14 right here. 3 meters. 14.3, and then a minimum at 20 hours after midnight at 0.2. So right here. So this is 20, 0.2. All right, so that's what we have so far. So that leads us into our first part, which is the maximum value is 3. Right? So we saw that from our maximum value given. Our minimum value is 0.2. So our A value is 3 minus 0.2 divided by 2. So A equals 1.4. Okay, that's our first part. Okay, from the A value, I have my equation. The maximum value equals D plus absolute value of A. Maximum value is 3. D is what I'm looking for, plus absolute value of 1.4. My D value is 1.6. Okay, 1.6. Let's think about our period. So what do we have for our period? So we know this, from max to min, right? So from 3 to 0.2, from max to min, That is 6 hours. We know that when we go from max to min, right? When we go from max to min, that is half a period. Okay, so this is half a period. So a full period is therefore 6 times 2 equals 12 hours. So our period is 12 hours. Okay? Let's determine our b value based on a period of 12. So b value that is period equals 2 pi divided by absolute value b. Period is 12 equals 2 pi divided by absolute value b. That's b equals 2 pi divided by 12. B equals pi over 6. Okay, there's our b value, pi over 6. All right, let's find our c value. C value, and this will lead nicely into determining our first equation. So let's think in terms of the cosine function. Okay, so I'm going to graph this first, right? So every 6 hours I have a max and a min happening. So my other min would be right here. Okay, and then the other max would be at 2 hours after midnight at 3, so 2 and 3. Okay, and then our other max would be at 26 hours, so 26 hours and 3. Okay, if I roughly sketch this out, something like this. And so on, right? I'm going to look at this key point right here, folks, right here. I know cosine starts here. I'll call this point A. Cosine function starts here. Okay? What is this phase shift right here? From cosine that way to this point. Well, that is exactly 2 hours, right? So for the cosine function, my c value equals, so cosine function, to get to the from A to, let's say, B. So this is B. From A to B, right? Phase shift 2 units to the right. So 2 hours to the right. So my c value equals a positive 2. Okay, so now I can write my cosine function. So let's write that. Y equals a cosine of b, x minus c plus d. Let's fill in all our values. Y equals, a value is 1.4. So let me highlight all these. Okay, 1.4 cosine of the b value, which is pi over 6. Cosine pi over 6 x minus c, which is 2, plus d, which is plus 1.6. Okay, so that's our cosine. I need 4 different equations. Yeah, 4. All right. One thing I forgot to do is I'm going to sketch in my sinusoidal axis. So my sinusoidal axis right here, folks, is at d equals 1.6. So 1.6. I'm going to sketch that in right there. Okay, d equals 1.6. Okay, for my sine function, y equals sine a sine of b, x minus c plus d. The a, b, and the d values are the same, but how do I get my c value? So let's think of it this way, all right? From this graph, right, I can get more exact points. So if I go down, I have this point right here on the graph. I'm going to call that point D, and I'm going to call this point C. So I know from point C, I have the start of my sine function right here, right? My sine function starts right there. So from C to D, so let me go back and finish this discussion. So you saw the graph up there. From C to D, I do a horizontal phase shift. So phase shift. 1 unit left. Okay, so from sine, I need to go this way, folks. 1 unit left. Okay, so 1 hour left. 1 unit left. 1 unit left. Okay, so C equals -1 in this case. All right, so y equals A, which is 1.4, so we're doing sine this time, sine of B, which is pi over 6, times x minus -1, which is the same as x plus 1, and then plus 1.6. Okay. The other way you can think about it is this way, right? Remember, what's the period? Period is 12 hours, right? So we know the period is 12 hours. When we go from cosine to sine, what's that phase shift? It's 1/4 times 12. That's a 3-hour phase shift. Okay, cosine, you would have to phase shift to the right. Sorry. Yeah, so it's a phase shift of 3 hours. And so the sine function would have to shift 3 hours or 3 to the left, right? So let's think of it that way. Okay, so 3. So if I take this one right here, so if I take over here, y equals 1.4 cosine of pi over 6 x minus 2, and then I shift it by 3 hours to the left. That's a c value of -3 plus 1.6, right? And remember, when I shift it, I'm making an equivalent sine function, right? So I'm going to make that into sine. Okay? Y equals 1.4 sine of pi over 6. X minus 2 minus -3, that's x minus 2 plus 3, that's x plus 1, and plus 1.6. And that is the same, in fact, what we have here. So this is the other way to think about it, is this relationship when you phase shift from cosine to sine or sine to cosine. It's 1/4 of the period, and you adjust accordingly whether you're moving left or right. Okay? All right. All right. I'm gonna erase all this because I just need to make room, folks. Okay, so you got that. There's two ways to do it actually. Okay, let's continue. I have two more ways to do this. I'm just gonna carve out this part for the last sentence here. The last part. When a is less than 0. Okay, so in other words, when a equals negative 1.4 in either case, I'm going to start with a cosine function. Y equals 1.4 cosine pi over 6 times x minus 2 plus 1.6. Okay. You can do this graphically, or you can think about it using that wonderful trick you did when you take the cosine and you make the a value negative. What do I need to do in here? What happens with the phase shift so I can match the equation, right? So what is C value to match my graph, right? So we need to adjust the C value to make sure the graphs match. Okay, we know that when we multiply by a value of -1, right? So we got a equals -1.4. I take my period is 12 hours, and I multiply by 1/2, and that's 6 hours. So I can either go left or right, okay? And either case, whether I go left or right, it's still the same phase shift, so it's a minimum phase shift, so the phase shift is minimized. I can go left or right by 6 hours. So in this case, let me go left by 6 hours. Yeah, if I go left by 6 hours, so let's hold on to this. Okay. So y So what do I need to do here? I need to x minus 2 minus, I'm going to shift by 6 hours to the left. So that's a C value of -6 plus 1.6. So all of this becomes y equals -1.4 cosine of pi over 6 x minus 2 plus 6, that's x plus 4, and that's plus 1.6. Okay, so that is the equivalent cosine graph when a is less than 0. Okay, we're using this handy little trick here. Okay, and then let's do the second part, which is the sine. Okay, so when I have y equals 1.4 sine of pi over 6 x plus 1 plus 1.6. Okay, I want to make it a negative a value. So I have negative 1.4 sine of pi over 6. And then what is this phase shift? So what is C value to match my graph? Okay, I'm going to use this relationship again. When I go from cosine of x to negative cosine of x, or sine of x to the negative sine of x. The phase shift is related to this. So this is the period. And then I multiply by 1/2 because when you go a value, when you reflect the sinusoidal function, it puts it out of phase by half of the period. So I go period times 1/2 equals 6 hours. And in this case, I need to adjust my C value by 6 hours. Which way? Left or right? Does not matter, right? Either way is a minimum phase shift. Okay, so when I do that, what happens? So I need to phase shift. Let's go. I'm going to go. Let's go to the right, 6 units to the right. Okay, so I'm going to go x plus 1 minus 6 units to the right. Well, that is just x minus, let me just write this a little neater, x minus 5 plus 1.6, and that is the equivalent equation. So you have 4 different equations, and I'll leave it to you. I'll leave the link in the class notes or on D2L. You can check these 4 equations to see indeed, or you can graph them on your calculator to see indeed, are those 4 equations equivalent? Will they produce the same graph? Okay? All right. One last part here. Over what domain is the function valid? Well, tides, let's just make a statement. Tides vary every day. So tides are cyclical, meaning they'll be about or approximately at the same point roughly every day of the year, but they vary every day. They're not exact, right? But we've made an assumption that this is a perfect sinusoid, so we can answer these questions, right? Tides vary every day and are affected by many factors, okay? This particular function, the way we've graphed it and the way we set the parameters, this particular function is valid for a domain of t such that t is greater than or equals 0 but less than or equal to 30 hours, and t is an element of all real numbers, because who knows what it'll be tomorrow, right? But we know for sure that the domain is valid for 0 to 30 hours because this is how we've defined the problem for this particular day at this particular afternoon in somewhere in Victoria, BC. Okay, number 2, we got the Singapore Flyer is the world's tallest Ferris wheel. I think that's still true. Okay, people ride the wheel in capsules. The wheel has a diameter of 150 meters and completes 1 revolution in approximately 32 minutes. A capsule reaches a height of 165 meters. Okay, so that 1 revolution in 32 minutes, that's your period, folks, right? How much time does it take to start at one point and come back exactly to that same point? So if you think about it, this is like your classic, I'm going to graph the unit circle. Remember that animation I showed you, unit circle, and what does it look like on a Cartesian graph? Okay, so there's my period. Let's sketch this diagram. So 32. Okay, I'm going to sketch one diagram, 1 revolution. 32, my x-axis is time in minutes, and then the y-axis is height in meters. Okay, there's my Ferris wheel. I'm going to outline the circle, so I purposefully put the picture of the Ferris wheel, that's actually the Singapore Flyer, on the left side, line it up with the graph and show you where the circular parts of the circle, so the various parts of the circle, how it corresponds to the Cartesian plane. There's the minimum, and that's at, it says, yeah, So there's the top and the bottom. So that's going to correspond to the minimum and the maximum. So what is that? The maximum, we said it reaches a height of 165 meters. There's the diameter of the wheel, and it's 150 meters, so 165 minus 150. What's the minimum point down there? It has to be 15 meters. Okay, so there's our max and our min, 165 and 15. Okay, I'm going to divide the time axis, the t-axis, into some of the key points that are going to correspond to the time related to where we are on the wheel itself. Okay, so I'm going to divide it first in half, and then I'm going to divide it into quarters. Okay, so 4, 8, 12, 16, and then the same thing on the other half. Let's divide it into quarters. 16, 20, 24, 28, and 32. Okay, and we're graphing one complete cycle, folks. So what does that look like? Okay, as we graph this, I'm going to divide this circle into quadrants and then graph the key quadrant points along the Cartesian plane. Okay, so I'm starting at a minimum of 0, 15. That's our starting point. That's the beginning of our revolution at the bottom of the Ferris wheel. Okay, there it is. That's our start. And then as the wheel turns, we get to that first 90-degree point. Okay, before we do that, let's draw in. I like to draw in these lines, dotted lines, as like guide points or like reference points. So let's draw in the minimum all the way across. Okay, that's 32, 15. So at 32 minutes, we're back down to 15 meters above the ground. There's our maximum. The maximum has to occur right in the center, so halfway through the period at 16 and 165. So there's 16, 165, and that corresponds to a maximum at 16, 165 on the Cartesian plane. Okay, let's look at the first quarter of our circle. So I'm going to go dotted line. What is that point? Okay, what's the halfway point between 15 and 165? Let's do a little bit of math and think about that's a difference of 150. 150 divided by 2 is 75, and I add 75 back to 15. So 15 plus 75 is 90. So let's label 90 as that midpoint where it's at 1/4. Okay, so there's 150. That's the diameter of the wheel. So halfway, if you split it in half, the radius of the wheel is 75. So 15 plus 75 would be 90. So halfway in height is 90. And let's draw that reference point all the way across. And so halfway up in height, so at 90 meters, as the wheel rotates, we get up to 90. And what's our point for 90? Right at 8. Okay, so 8 minutes, that's halfway between the first half. So between 0 and 16, halfway is 8. So halfway in height is 90. And I can do the same for the other side. 24 and 90, halfway between 16 and 32 is 24, and halfway in height is up to 90. Okay, so I have 8 and 90. So that's 8 and 90. And then the other side, symmetric point, is 24 and 90. Okay, remember that's 90 meters, so 24 minutes, 90 meters. And then I think I got, let's see, I got all the key points that I need. Let's draw a nice smooth curve. Okay, there we go, the other side. And there's a diagram for the Singapore Flyer for 1 full revolution. Okay, and then the midline, we'll write that down later. That's the sinusoidal axis, that's the midline. Okay, let's go to part B. Determine the 4 different functions that model the height h meters of a capsule at any time t minutes after the wheel begins to rotate. Okay, so this is, I think, is the more challenging part. Let's write the general equation here. I'm going to start with the sine function, right? So y equals a sine of b times x minus c plus d. It says in terms of h and t, so I'm going to rewrite this as h equals a times sine of b times t minus c plus d. So I'm going to use the variables that are given for this problem. Okay, what do we want to start with first? Let's find our a value. I know I have a max value of 165 meters. Okay, and then I have a minimum value of 15. That is the max and min height of the Ferris wheel. So my a value is 165 minus 15 divided by 2. And what do I get for an a value? A equals 75. Okay, let's talk about the b value. Actually, no, let's talk about the d value. Sorry. D value. Max equals d plus the absolute value of a. So let's do some substitution. 165 equals d plus the absolute value of 75. Solve for d. What do you get? So that's where I get my a value. Solve for d. I get d equals 90. Okay? And where is that? Well, that's d equals 90. That's my midline, folks. That is also my sinusoidal axis. That is also my vertical shift. Okay, so that's the d value. I have a value, d value. What's next here? Now let's do b value. B value. I'm going to think about b value in terms of period. I know the two are related. So period is 32 minutes. Well, how do I get the b value? Well, period equals 2 pi over the absolute value of my b value. So I set 32 equals 2 pi over b, solve for b, and I get pi over 16 for my b value. Okay, next, c value. I have to think about my phase shift. So I'm going to think of that about my phase shift from the point of view of a standard sine function. So go to the midline, okay? And I'm picking that point 890 on the midline, or the sinusoidal axis. I'll call that point A. And I'm going to go to the h-axis, which is at 090, and I'm going to pick point B right there. Okay, so point B right there. And I'm going to sketch in what a sine function would look like from point B. So it would look like that. Okay, and then I'm going to think of from point B to point A, what is that phase shift? Well, read it down there. From point B to point A, that's a phase shift of 8 minutes or 8 units to the right. So that's my horizontal phase shift just by graph reading. So what's my c value then based on a horizontal phase shift? So let's write this out. So from point B to A, So that's 0.090 on my sine function to 890. What is my horizontal shift? Well, my phase shift, I'm reading it, going from 0 to 8, that's a phase shift of 8 units or 8 minutes to the right. So what is my C value? So the C value equals positive 8. All right, so now I have all 4 of my transformation values, A, B, C, and D. So let's put some boxes around that. And let's start thinking about our equation. The first one that we'll do, number 1, y equals, or let's say h equals, so height equals 75 sine of pi over 16, which is my b value, pi over 16, which is my b value, times time t minus, what's my phase shift? 8 to the right. And then what is my d value, my vertical shift? Plus 90. Okay, so that is my first equation based on the A, B, C, and D values that I generated. Okay, number 2. H equals, okay, what I'm going to do the negative a value of my sine function. So if I make a negative, so negative 75 instead of positive 75, I get sine of pi over 6. So I get h equals negative 75 sine of pi over 6. Well, what will I put in the middle as my phase shift when a is less than 0? So let's think about this. Okay, so pause and think. How will I change? So I'm going to take t minus 8 from equation 1, and I need to add or subtract the appropriate phase shift so that I can make an equivalent graph in terms of this sine function where a is less than 0. Okay, so what will I do here? So I start with t minus 8, and what will I add or subtract? So t minus 8, should be, it's not minus 8, folks. That's a mistake. Let's back that up, because we are talking when we make a less than 0, we need to think in terms of half of the period, not quarter of the period. So that's a mistake. So let's erase all that. So it's t minus 8. What do I add or subtract for an equivalent function here? So it's h equals negative 75 sine of pi over 6, t minus 8. So I'm going to think about my period here. Let's sketch this out. Period equals 32 minutes. Well, when I have a reflection or when I make the a value negative, I'm going to multiply by what? A factor of 1/2. So what's 1/2 of 32? It's 16. So 16 is the number, the magic number that I'm going to think of to adjust my sine function when a is less than 0. So I can either do two things. I can shift it 16 units to the right by saying minus 16, or I can shift it 16 units to the left by saying minus negative 16. So those are the two ways. Remember, I can go either left or right, but I want to choose the correct version. So I have two choices. I want to choose the correct one that gives me a minimum phase shift. So if I look at the second one that I drew an arrow on, that's t minus 8 minus negative 16. That's t minus 8 plus 16. That gives me t plus 8 versus t minus 24. So I'm going to pick t plus 8. That's going to give me my minimum phase shift. So t minus 8 minus negative 16. Okay, and then when I clean that up, what does that become? That's t minus 8 plus 16. That's going to give me t plus 8. And then let's throw that plus 90 back in. So that's a minimum phase shift. So Equation 2 is h equals negative 75 sine of pi over 6 times t plus 8. There's the appropriate phase shift, plus 90 to give me the equivalent equation in terms of a is less than 0 for the sine function. So number 3, h equals 75. Now we're doing cosine of pi over 16. So remember, a, b, and d values are all the same. So t minus 8, I'm going to leave a big set of brackets, t minus 8, and then that's plus 90. So a, b, and d values are all the same. What will I choose as my phase shift when I write this equation in terms of cosine, right? So when I take the sine function and write it in terms of cosine, what do I need to adjust by? Remember, it's the period, 32, and it's 1/4 of that period, because cosine and sine are always 1/4 of the period out of phase. So what's 1/4 of 32? Okay, that is 8. So 8 minutes. So 8 is my magic number. Which way will I shift it? So if you think about the position of cosine and the position of sine, cosine leads sine. So meaning, I think of the cosine at a maximum value right on the h-axis. I need to shift it 8 units, right, to match the sine function. So I do minus 8 because it's 1/4 of the period out of phase. So it's t minus 8 minus 8. If I clean that up, what do I get? T minus 16 plus 90. There's my third equation. Okay, number 4, I'm going to do this case where I'm going to take number 3's equation and I'm going to say a is less than 0. Okay, so I'm going to reflect it. And so I get h equals negative 75 cosine pi over 16 times t minus 16. And I'm going to leave a space there, and plus 90. What do I have to phase shift this by? T minus 16 to match the original graph. So remember, it's anytime I do a is less than 0, so the negative a version, I take half of the period, so half of the period is 16, and that's how much out of phase it is. So I have to adjust it by 16. Well, remember, I can go left or right because it's an exact, like, I can go left or right, so I'm going to adjust it by either minus 16, so minus 16, or minus negative 16. I'm going to choose the one that gives me the minimum phase shift. So let's do both cases here. That second one, t minus 16 minus negative 16, that's t minus 16 plus 16. That's t plus 0. So that's going to be my minimum phase shift, whereas the first one's going to give me t minus negative 32, or t minus 32. Okay, so let me pencil that in. T minus 16 minus negative 16 plus 90. Okay, let's clean that up. That's going to be t minus 16 plus 16. That's t plus 0. So let's clean all that up. T, so it's just t, and then plus 90. Okay, and that's our fourth equation. Okay, look at all that work. 1, 2, 3, 4. Go ahead and take a moment and go to decimals and graph those 4. Make sure those 4 make sense. In fact, I think I have a decimals for you after this, after we're all done, to show you that those 4 actually line up and make sense, okay? Letter C, assume a capsule is at the base of the wheel when it begins to rotate. Use technology to graph the function. So this is what I'm showing. There's technology to graph the function. Then estimate the height of the capsule 20 minutes after the wheel begins to rotate and give the answer to the nearest meter. Okay, so a little bit of technology use, graphing, just recreating what on my graphing calculator, the problem or the sketch that I had. Okay, so a minimum of 15, maximum of 165. That 143, I'm kind of skipping ahead here. Let me just label some more key points. The maximum occurs at 16 minutes. That 143, if I draw it all the way across, okay, that corresponds to 20 minutes after the wheel begins to rotate. So if I think about using the trace function. So if I tell you 20 minutes, that's the t value or the x value. If I trace 20 on my graphing calculator, x equals 20 minutes, the y value that it returns is 143, or a height of 143 meters above the ground. Okay, so we are on Desmos to visualize what we did in our last word problem here. 75 sine of pi over 16 times theta, or x minus 8 plus 90. So those are that was the first equation that we generated, a, b, c, and d values. Okay, so we see that we have a minimum point at 0, 15 and a maximum point at 16, 165, and that's what we predicted with our graph, our max and min points for the Ferris wheel. And then if we keep going, there's 32, 15, and that shows us that we have a period of 32, right? 32 minutes. Okay, so now what we're doing is we're creating the sine graph of this function where a is less than 0. So when a is less than 0, so we'll put in a negative sign there, it shifts the graph out of phase by 1/2 of the period. So if the period is 32, then half of the period is 16. And you can see clearly that from 0, 165 to 16, 165, we are out of phase by half of the period. So how do I make the two graphs the same? So how do I adjust the blue graph, y equals negative 75 sine of pi over 16 theta minus 8? Well, I'll show you two ways to do it. We want to do it in the ways that minimizes the phase shift. So I can do minus 16 or minus negative 16. So I go to the right by 16 units, or I go to the left by 16 units. Remember, I can do either or because it's an equivalent phase shift, but I want to minimize my phase shift. So I'm going to go to the left by 16 units minus negative 16, and that makes it a plus 8 total. Okay, so that's the sine version. Let's go to the cosine version. So I'm going to create a third graph, and let me insert a cosine in there. So when I do that and I turn the graph on, what happens? Let's see. So I have y equals 75 cosine of pi over 16, and it is out of phase from, look where the maximums are, 8, 165 and 16, 165. So we said the period is 32. So if I take a quarter of the period, that is 8 units, I'm out of phase by 8 units from the purple graph to the blue graph. So what does that mean? I need to shift it to the right by 8 units. So the C value is positive 8. So it's minus 8. So it's theta minus 8 minus 8. And that's what we end up shifting it. So let's take a look here. Okay, so we're going from 8 Okay, so I'm going to throw in the sinusoidal axis just so we know where the function starts. Okay, there we go. Okay, so let's take a look at our phase shift. So I'm going to go, what did I do here? Theta minus 8 minus 8. Okay, and that lines it up and matches. So that's a phase shift of a quarter of our period, so 8 units to the right, so C equals positive 8. Or we want to minimize the phase shift. So what are we doing here? I think I'm going to show you, right? We can phase shift it by 3/4, right? So minus 24, 3/4 of a period to the left, but that doesn't minimize our phase shift. If I do that, that's going to be a positive 16. Okay, so I'm going to end up, okay, what do we, yeah. So I'm just going to shift it to the right by a quarter of a period, and I end up with theta minus 16. So y equals 75 cosine of pi over 16 times theta minus 16 plus 90. So the last part is what happens when I make my cosine value, sorry, the a value of the cosine version. What happens when I make it negative? So let's throw a negative in there. Turn it on. It's out of phase by, so from 0, 165 to 16, 165. That's half a period. So I know that when I make the A value negative, I put it out of phase by half of the period. So I need to adjust it by half of the period. Well, left or right, you can go either way, but we want to minimize the phase shift. If I go to the right, so what am I doing here? Let's see. If I go to the right, let's see what I do here. Theta minus 16. Okay, so I'm going to the right and the graphs match. That's one way to do it. But am I minimizing my phase shift? That would make it a minus 32 for my phase shift. Okay, what if I go to the left, where I go minus negative 16? That also matches the graph. Am I minimizing my phase shift? Well, if I do the math in the brackets there, theta minus 16 minus negative 16, that's theta plus 0. So that minimizes my phase shift, right? So I'm doing as small a phase shift as possible. So, okay, minus negative 16. Okay, and then when I clean that up, what does that look like? Okay, that's just theta, right? It's 0 inside the brackets, just the theta version, and that is minimizing my phase shift. Okay, the pedals on a bicycle have a maximum height of 30 centimeters above the ground and a minimum distance of 8 centimeters above the ground. Assume a person starts pedaling with the pedal in its lowest position and pedals at a constant rate of 20 cycles per minute. State the period in seconds for this periodic function. Okay, so we have, let's start with 20 cycles in 1 minute. And let's do some unit analysis here. Multiply by 1 minute divided by 60 seconds. So that's our conversion factor. We want cycles per second. And that equals 20 cycles in 60 seconds. Well, what is period? Right? Period is the number, or period is the amount of times in amount of time in one cycle. So if I just flip it over and I just say it's 60 seconds in 20 cycles rather than 20 seconds in 60 seconds, I can say 60 seconds divided by 20 cycles, that's 3 seconds in one cycle. So the period is how much time for one complete cycle? 3 seconds. So the period is 3 seconds. Okay, sketch a graph of at least one cycle. So one cycle is 3 seconds. Okay, we know the maximum height. So the vertical axis, or the dependent variable, is height measured in centimeters. So it's 30 seconds is the maximum. And then on the independent axis, or the x-axis, is time, which is in units of seconds. Okay, so we have 30 seconds and 8 seconds, or sorry, 30 centimeters and 8 centimeters as a minimum. And then I'm going to graph at least one cycle. Okay, and then so I'm going to label it as 3 seconds and 6 seconds. Okay, looks like it says graph at least one cycle. I'm going to graph 2 cycles, why not? So at this point, what have I done here? So I'm making some dotted lines as reference points. So right down the middle there, 3 seconds would be one cycle. I'm actually doing 2 cycles here, and I have 1.5 and 4.5 seconds on the time axis. Okay, so let's start labeling our first couple points here. I have 0, 8. That's the starting point. Then I have a maximum occur at 1.5 seconds and 30 centimeters. So the pedal is at the highest at 1.5 seconds. And I know that because it's halfway through my cycle, my maximum occurs. And then on the downswing there, all the way down to one complete cycle and back to a minimum at 3 seconds. So 3, 8. And then just let's repeat one more cycle here. All right, there we go. Okay, and so we have sketched a graph of at least one cycle, and that 3 seconds, that is one cycle there where we start at 0, 8, reach a maximum of 1.5 and 30, and then back down to 3, 8. Letter C, determine an equation for the height of the pedal above the ground as a function of time in seconds. Okay, so let's start looking for our A, B, C, and D values. So the A value I'm going to develop by thinking about max of 30 centimeters, min of 8, and I use my equation for amplitude, 30 minus 8 divided by 2. And so the A value I get is 11. Okay, so that's my A value. Next one, let's think about our period. So I know my period is 3. That's what we calculated from above, that 20 cycles per minute. So I'm going to use my equation, period equals 2 pi divided by absolute value of b. So 3 equals 2 pi divided by absolute value of b. My b value is 2 pi over 3. Okay, next one. Let's get the vertical shift. So maximum value equals the vertical shift d plus the absolute value of a. So 30 equals d plus absolute value of 11, solve for d, and I get d value of 19. That's my sinusoidal axis. So let me label that as my sinusoidal axis at 19. Okay, d equals 19. Okay, so I have d equals 19. From 19 to 30, that's a value of 11. And then from 19 to 8, that's a value of 11. So I know that works. Okay, so that's a sinusoidal axis. Back to letter D. Actually, letter C. We need to figure out the C value, the horizontal phase shift. Okay, so let's think about, so let's go back up to our graph. And I'm going to do this in terms of the cosine value. So in general, I'm going to start with y equals a cosine of b times theta minus c plus d. And let's think about where cosine would start. Okay, cosine would start right on our h-axis at point A. So what is that phase shift? So I'll draw in the cosine in blue there, and I want to go from A to B. So you can see my cosine function. What is that? That's a phase shift of 1.5 to the right. Okay, so let's finish this off. So the C value is 1.5 to the right. So the C value is positive 1.5. Okay, now I have my A, B, C, and D values. And let's plug it in. So y equals 11 cosine of 2 pi over 3 in brackets times theta minus 1.5 plus a D value of 19. There's my equation. Okay, use your equation to determine the height of the pedal after 4 seconds. So I'm going to take my equation and turn it into a function by saying f of x equals 11 cosine of 2 pi divided by 3 theta. In this case, let me say x, this is a function of x. X minus 1.5 plus 19. So f of 4, okay, what is the height of the pedal after 4 seconds? 11 cosine of 2 pi divided by 3. Okay, and then plug in x equals 4. 4 minus 1.5 plus 19. Okay, the rest is arithmetic. Let's take a look at this. F of 4 equals 11 cosine of 2 pi divided by 3 times 2.5. 4 minus 1.5 is 2.5 plus 19. Okay, let's keep evaluating. F of 4 equals 11 cosine of 2 pi divided by 3 times 2.5. That is 5 pi over 3 plus 19. Okay. Don't use a calculator, folks. I want you to think about exact values on our unit circle. What is cosine of 5 pi over 3? So pause here and think about it. Do not use calculator. That equals what? 11 times, what's cosine of 5 pi over 3? Think. Okay, do you got it? 11 times 1/2, yep. So that's in quadrant 4, cosine of 5 pi over 3 is positive. So 11 times 1/2 plus 19 equals 5.5 plus 19. So my pedal height in 4 seconds is 24.5 centimeters. So at 4 seconds, the pedal height is at 24.5 centimeters. Okay. Last one. Use your graphing calculator to determine the length of time to the nearest hundredth of a second that the pedal is above a height of 25 centimeters above the ground for each cycle. Okay, so basically it's asking how much time in one cycle is the pedal above 25 centimeters. So on your graphing calculator, you can graph the function that we determined. So it would look something like this. And then I'm going to graph y2 equals 25 centimeters. The graph in red is your cosine function. Y equals 11 cosine of 2 pi over 3 times x minus 1.5 plus 19. So there it is. Okay, once you have those two graphed, you know what's coming up next. I need to find those two intersection points. So just let's hang on here. Okay, so we got the two graphs. There's my two intersection points, and I calculated that to be 1.0254, x value and y value of 25, of course, and then the second intersection point at 1.9745 and 25, and then the time value. So I'm going to take those two highlighted values and subtract the two, and that will give me a time value for how much time the pedal was at or above 25 centimeters. So 1.9745 seconds minus 1.0254 seconds, that equals 0.95 seconds. So let's make a statement here. Okay, what does 0.95 seconds mean in the context of this problem? It means the pedal is above 25 centimeters for 0.95 seconds. So the pedal is above 25 centimeters for 0.95 seconds per cycle.